I also had a, once we come back, it will get happy. I also had this example done and I put up a little video for that. But you should be able to do it first to get a feel for how things work. Okay. Are there any questions on what we have discussed or anything else? Okay. So today is, I guess, the penultimate, the last part one class. The main topic that I'm going to try and complete is essentially go from game tree search, a little more about the game tree search, and then sort of segue from there to the idea of handling stochastic words using the same kinds of techniques, and also in general supporting online search, where you need to make decisions under time pressure. You don't just get all the time to make your decisions first. Okay, so that's what I'm going to discuss a little, and then depending on how that goes, I might be able to talk a little quickly about first order logic. However, that's mostly just sort of to say that I've given you some idea. I don't think I'll have the time to actually do justice to first order logic in the class. Okay. This stuff, the game tree stuff, is still fair game for the exam, for the final exam. So the good news is that the final would be take home. It looked like good news or bad news? I don't know. I mean, I feel as if people have done better when they did the exam at home than the 2 times they did it in class. So I am going to make the final take home. It's sort of going to be around the same. It may be longer, but would be the same type of questions. Okay, and since there are at least parts of the topics, I mean, and it'll also be more geared towards the topics that we haven't tested on. So for example, the entire learning, the game trees, would be definitely getting more play. But then since it's going to be a comprehensive, there could be questions from before too. Since it's take home, of course, you can always just wait until the exam is given and start, desperately figuring out what it is, which is why I guess I have to ask everything so that I'll make you read everything. But anyway, so I think it's going to be a take home, and then it would be given in such a way that it'll still be due the same day the final exam would have been. I'll give you the exact details, next week. Okay. I think the expectation was that the scheduled final was the Tuesday after next. So the take home will be over by that time. That's basically the way. But I might give you just before that, maybe on Monday, and ask for Tuesday or something. Okay. But one other thing is that you will all be, I'll be sending a mail, you'll all be required to take part in a mandatory exercise on interactive review, where essentially I'll send a mail asking you to write down 5 things that you learned that caught your attention, okay, in the course. And then you answer that basically as a comment to that on the blog. You just write the 5 things that particularly struck your fancy. Okay, it doesn't really matter which 5 things struck your fancy. You can just talk about what you liked. And my general experience has been that the catalog of those actually gives me what got through and what people actually cared about. And then for you also, since I might be telling you that you should care about this topic, and you may or may not care about it. But if lots of your fellow students thought that was a pretty important topic and you didn't think it was, then you might second guess your decision. Okay, it shouldn't take too much time, but it has to be done. I'll send a mail, and it has to be done before the final class starts, which will be next Tuesday. Okay, so and that will actually become sort of a review that you could have looked at it yourself. I haven't completely decided what the topics for the final class would be. Probably I would and I would have to do something more about logic, and then some mini review of the class. So that's what it's going to be. Okay. Any questions? Okay. So we were here last time, just towards the end of the class. We figured out how to do alpha beta search, and then we did, however, realize that going too deep, actually doing min-max search, even with alpha beta pruning on the entire tree, where the leaf nodes are definite terminal positions for the game, is just infeasible for any realistic game. Okay, so basically, because of that, you have to, since you don't have the time to even generate the entire search tree, okay, I mean, you can't evaluate it, okay? So the question then is, what will I do to get some reasonable move going? And the idea we had was that we just go some levels deep, okay, and then apply an evaluation function to the final, the leaf nodes. And the evaluation functions normally will say, if it is for sure a win, realize that it's a win. For sure it's a loss, realize that it's a loss. If not, it's a heuristic estimate of the value of that particular game to the max agent. Okay? And as I said, for, I mean, obviously this is game specific, just as general heuristics are, you know, for search are problem specific. Okay, here too it's game specific. Okay? So you care about, in this case, you know, for the tic-tac-toe, we considered an example was the number of rows, columns, diagonals that are open for one minus the number of rows, columns, diagonals that are open to the other. Okay, and that's your relative advantage for that particular game position. Okay, and then for chess, of course, a lot of people have spent a lot of time on these evaluation functions. For chess, for example, you might say, it would be some sort of a weighted average of variety of, you know, the board position properties, such as the control of the center, the number of, you know, number of queens you have left, which will be either 1 or 0, and then things like that. Okay, and then you need to then figure out these weights. As I mentioned last time, you could potentially learn these weights if you have enough number of training examples of board positions, and from there, whether grandmasters were able to win or lose, then you can use that information to actually learn something about, you know, what features seem to matter more and which should have higher weights. Okay, but I'll also tell you in a minute actually a better way to improve your estimate of the goodness of a board position in a minute. But you know, so this is what you would apply to the leaf nodes, right? Okay. So then once you do that, then in essence, basically you just run min-max search on that. Okay. So so basically, if you have enough time to go, let's say 12 ply in chess. Okay, even if in fact at the 12th ply, there not all the nodes are leaf node, I mean not all the nodes are terminal positions. If you just apply the evaluation function to those leaf nodes, okay, and then you back up the values using the same min-max search, then you can pretty much get an extremely good performance. Essentially, you can get as good a performance as, you know, close to human grandmasters. For chess, of course, going 12 ply would be still very costly, and that's why, in fact, I mean, Deep Blue was using essentially dedicated hardware in '97. Okay, but now, of course, I think you probably don't need dedicated hardware. Even, you know, it's probably more powerful computers are available just to you and me right now. At the time when Deep Blue was playing Kasparov, they essentially had a VLSI chip which just generates chess moves very fast and evaluates them. And it's IBM. If IBM wants to do it, it'll do it. Okay. Right? But I mean, so that gives you a good idea. Now, the one interesting question, of course, is how deep should we go? Right? As this basically tells you the deeper the better. Right, because you only look at 4-ply, then it's a hopeless chess player, whereas 8-ply you'll get a reasonable human play, and 12-ply you'll get too close to grandmaster for chess, at least. Now the interesting question actually is, how many of you are worried as to why going deeper is better? I mean, do people think it's intuitively reasonable that you look ahead more, it should be better? Or you are skeptical about it? In particular, the question is, it turns out that, we'll come back to this slide in a minute, but, it turns out that there could be two different reasons as to why going deeper helps you. Remember, the whole point of it is you go deeper and then you do min-max search, okay, and then you figure out your best move. And then you make that move. And by the way, just in case people didn't get it, all of this is to decide the current move. It's your time right now, so you look at the board position, you generate whatever, let's say 12-ply search tree, okay? You do min-max, alpha beta pruning, figure out what's the best move that you're going to make. You'll say, okay, I'll make this move. And then now your opponent gets to do it. Your opponent is human, they'll probably do whatever they want. If it's a computer, probably it does similar search, maybe with a slightly different evaluation function. And then your opponent makes the move. And after your opponent makes the move, then you get to make the move. And when it becomes your turn, you start all over again. Essentially, you generate from the new board position, you generate your game tree again. 12-ply D, okay, and then see what's the best move. Notice that had it been the case that from the move, from the current position A, you generated the entire tree such that all of these are terminal positions. Suppose you did that, okay? And then you figured out that I'm going to make this move, okay? And then the opponent made that move and you are in this state. There wouldn't have been any real reason to regenerate the tree because the state under this would be like that. The tree under that would be like that, right? Because you generated the entire search tree. But if I'm doing only 12-ply deep, that's no longer true because basically 12-ply deep, I may have only looked up to this position before. Now that I'm focusing on this, I can go up to that much. I'll go deeper. Now that I know I'm in this state, I will spend more time figuring out what's the best move. So this is why essentially every time you restart your search and figure out your best move. Okay, that's what you're doing. Yes.
You can continue from that place.
Which one?
You have a 12 cutoff at that place.
Yeah, but then if you want to continue from here, then you have to remember this much.
But won't alpha beta pruning avoid you can't continue from there?
I didn't understand.
If you do alpha beta pruning, you actually don't know all of those states, right?
If something was pruned by alpha beta pruning, yes, you can then avoid. So his point is, suppose it turned out that there is, I think that's what he's trying to say. Suppose it turned out that underneath this move, there is a move below which the entire tree, you cut it off using alpha beta pruning before. When you cut off a subtree, you don't really care what's in it. That's the whole point. The tree being cut off is cut off because it doesn't matter what is in it. It will never be part of the main plane. In which case, it will still never be part of the main plane. Okay, but however, most game tree programs don't do this. This is too much work to remember, bookkeeping from one level to another level.
So you would do the alpha beta pruning every time you ran?
Every time, yeah. Every time you do the entire thing again. You start from the current move position that you are in, and then do the game tree and do to whatever depth you want. Okay, so the question, of course, as I was asking is, why exactly is it that going deeper is better? Okay, there could be two possible reasons as to why this could be. Okay, notice what's happening. Essentially, when you are, so the point, this was something that you would not have asked before, but now I can ask. Before, in the pure min-max search, if you are in a particular position and you have, these are your moves, okay, 1, 2, 3, you really still have to continue, growing them all the way until every leaf node is a terminal node. Now I told you that nothing has to be a terminal node. You can just take the node and apply an evaluation function and see how good it is. So why am I not applying the evaluation function here itself? That's my question. So you are essentially agreeing with me that rather than apply evaluation function here, I would like to go much deeper, apply evaluation function here, and then back up. So in some sense, when I back up the values, so this guy, this node, can be given a evaluation function value and a backed up value. We are believing that the backed up value is better than its evaluation function value. That's what we are believing. That's the reason why we think going deeper is better. Do you understand what I'm saying? So the assumption is that the evaluation function, which is sort of like the heuristic in your search, it's sort of doing shallow analysis. Whereas if you had gone below that node and did the shallow analysis here and backed it up using min-max, then the backed up value would be more closer to the true value of this node than direct application of evaluation function. That's what we are trying to say. I want you to understand this because this keeps getting used in like 2 other ideas today. Okay? So you're just basically postponing the shallow analysis rather than do the shallow analysis here, you're doing the shallow analysis here. Okay? So now if I do shallow analysis here and back it up, and if the value I get here is somehow better than directly applying shallow analysis here, why is that the case? There are 2 possible reasons. One is that you somehow believe that taking some mins and maxes of the evaluation function improves the evaluation function's accuracy, just somehow automatically. Okay? That's like basically you are estimating, you have some sort of a poor estimator, and you are estimating here, and you're combining estimates by doing maxes and mins. And you are thinking somehow that that way of getting its value is better than directly estimating one. Okay? The other option, other way of thinking about it is that going, actually, so the first one, it turns out shouldn't make any sense from a statistical point of view. If you ever need to estimate something, you should estimate it directly. You shouldn't estimate something else and try to estimate this in terms of that, because that increases the noise in the estimate. Okay? People from statistics would consider this to be a cardinal sin to do this. If you want to estimate the sum of variables, try to estimate the sum directly. Don't estimate each of the variables separately and then sum them. Because then if you do it that way, the noise will get summed up. So this shouldn't make any sense at all. So in fact, doing this should have made, so going deeper from a statistical point of view, should have made the search be worse. And yet it actually is better in many cases. Okay? And the reason it is better has got to do with the second possible reason, which is that what happens when you go deeper is while the way of winning the game is, for most reasonable games we play, the ways of winning the game are deep down in the search. The ways of losing the game are shallow. Did you get this? I mean, to win the game, in a reasonable way, you probably have to do a large amount of moves in chess. If you want to lose it and you're clueless, you can get lost. You can lose it very fast. Basically, they'll checkmate your thing and you're dead. If you can't get out of it. So there will be, if there are traps in the game tree, the traps are obvious losses. Okay? Then doing min-max search, doing evaluation here and going up, in essence, is capturing those traps. Remember, whenever I see a node, if it is a definite loss, I will realize it. Definite win, I'll realize it. Otherwise, I will apply my shallow evaluation function. And it is the presence of traps that actually makes going deeper a better idea. So I'm sort of asking you to first question yourself, why does going deeper work? Okay, many of you probably will think, yes, if you look ahead more, then you should do better. But why? It's the real question is, after you looked ahead more, if you looked at k-apply, do you know the true values here, or are you still applying the same shallow analysis here? We are applying the same shallow analysis here. And the analysis is no better than before. It's just that if you apply the shallow analysis here, you do at least take into account the obvious traps. And that improves the accuracy of the backed up value. And in fact, there's been work that has shown that you can have game trees where if you don't have any traps, then going deeper worsens performance. Now you might ask, why aren't we playing those games? They're boring, right? Right? If there are games where the only time you will win is 18,000 moves later, then there's no fun in it. You have to somehow lose very fast once in a while so that, people who are clueless will get into traps and get out. Okay, so there is work that's been done long back called game tree pathology, where they actually made artificial games which nobody is playing, where in fact going deeper worsens the performance of the game tree, the performance of the agent. And so, in fact, the reason it is working in going deeper is working is because if there is a if there is a sufficient percentage of traps sprinkled over the world, then sprinkled over the search space, then going deeper and going up improves performance. Okay, this is like questioning what seemed like an obviously reasonable thing to do, and then realizing a better reason as to why it is a reasonable thing to do. Okay? Any questions on this? Okay. So this is about what depth we should go to. The next one is should we go to uniform depth everywhere, or should we go to different levels of depth? Okay. And I mentioned as I was ending last class that there is no reason to go uniform depth. You can go, for example, you can go basically, actually you can go like that. This is it's a non-uniform tree. Here it went deeper here, and here it stopped here itself. Now, how do you decide this? How do you decide this? Basically, the way to think about it is this way. As soon as you generated this tree, you have B, C, and D. You can right away apply the evaluation function to B, C, and D. Okay, suppose you applied evaluation function to B, C, and D, and then B was 7, it said B was 7, C was 4, and D was 10. That's what the heuristic directly said. Okay, now you basically went here one level below B. Now you can back up the value. Now when you back up the value, you actually get 4. Okay, in fact, let me make it this way. Let me make it. So when I back up the value to B, that's a slightly better estimate than the previous estimate. If this new estimate is close to the old estimate, I would say maybe my estimate of B's goodness has stabilized. So I won't necessarily have to go much deeper. If on the other hand here, for C, let's say one level deeper if I go, suddenly previously I thought it was 10, its goodness is 10, and then when I back up by one level, back up after one level, it becomes 2, let's say. That's a huge jump in the goodness. That means the game is sort of volatile there. So you want to go deep. Do you see what I'm saying? So you can decide this sort of dynamically. You might say, I will go at least, maybe 3 levels deep everywhere. And then Above that, I can go more if, in fact, the game has not stabilized on that branch. Do you see what I'm saying? Okay? And this way, you will get a non-uniform tree. And then on that, you do your analysis. On that, you do your min-max and alpha beta pruning. Okay? So go deeper in branches where the game is in a flux. So backed up, that means the backed up values are changing fast. So in fact, it's best to think of the evaluation function can be applied first. You will get an estimate. Then you can go one level deeper, apply evaluation functions to here, and then back up. You get a slightly better estimate. Go even deeper, apply evaluation function here, back up. You'll get a slightly better estimate. And the question is, if these estimates are sort of converging, then you would say, well, I won't go any deeper. Okay, so that's basically the idea of Poisson search. And in fact, as I'll say in a minute, while I said 12 ply is good enough for grandmaster level chess, in certain branches, Deep Blue went 40 ply. 40 ply. If it did across the board, it would still be playing today, the first game. Okay, but for certain branches, it could go deeper because they haven't stabilized, and so it would just go those parts deeper. Okay, so those are the things that I mentioned last time quickly, and I just basically wanted to mention again. Now, one other interesting thing about this min-max search with depth cutoff is that until now you have thought of algorithms which are basically all or nothing computations. Okay, so you want to find out, let's say, how do you find out? So remember, you did A-star search to figure out what should the agent do, what action should the agent do. To figure that out, you ran A-star search until it found the optimal path to the goal, and then told the agent just do the first action. You don't quite know how long A-star would take to come up with the first, the entire path. Until it comes up with it, you can't take the first action. In general, most computer science algorithms that you have done till now, they are all of this property. They all have this property that you give them the input, start the algorithm, and wait for the best. When it is done, you know the answer, full answer. If you control C in the middle, or you basically interrupt the program in the middle, you get garbage. You get nothing. It's all or nothing. Now, for an agent which has a large amount of time to make its move, this is probably okay. It'll start the program, keep drinking cups of coffee or sleeping and whatever until the program ends. And then it tells it the full optimal path and it just does the first action. But we talked about the point that, sometimes the agents basically might be in a situation where the next decision has to be made very quickly. So for example, if I'm on the university drive and I'm trying to decide what move to make, I'm in the middle of the road, I can't decide what's my optimal strategy, and if I take too long, I will get run over by a bus. Right? So I need to make decisions faster. So in online decision making in general, so until now basically the only approach you had for online decision making is reflexive. So if you're in the middle of the road and cars are coming, you and then try to do something random. And then hopefully with some random chance you'll survive, with random chance you die. Right? So we had fully deliberative end and fully reflexive, help me kind of end. There was no in between. Because for the in between to exist, you need to have computations that are flexible, that take the time that you give them and give you a reasonable answer. Do you understand what I'm saying? So I need computations that are flexible or anytime computations. That means you can give them any amount of time and they'll do the best with that time. Okay? And those kinds of computations are extremely useful because then it becomes easier to decide, okay, so it's like, who was this guy who used to say, let me a little think. Okay, so you give yourself, okay, let me think for 1 minute, that's it. So I don't need to think for 1 minute, and then my thinking has to stop after 1 minute. If I give myself 2 minutes, maybe I'll have a slightly better answer. And those are basically flexible computations. My question is, have you had any algorithms until now which will take just the amount of time you give them and do the best they can in that?
Bayes network.
What?
Bayes network learning.
Not Bayes network learning. No, learning is different. Learning basically depends on the samples. But actually, one which does have is essentially approximate inference in Bayes networks. That has this property. The more samples you give, the more samples you generate in the likelihood weighting, for example, the more accurate the distribution that you're inferring would be. And then the second example is the one that we saw today, basically. Okay, so one way you can play games is you give yourself, let's say, depth 3 cutoff, because you know for sure you will be able to do depth 3 cutoff. And depth 3 cutoff, figure out what's your best move. Keep it in your head. And then if you still have more time, then now increase the depth to maybe 4. Recompute your best move. Now this is your current move. And then if you still are not asked for a solution, then do even better, even deeper. Did I make any sense to any of you? Okay, so it's basically, I'm telling you that the deeper you go, the more accurate your decision as to which move is the best move to make. Okay, and so you can decide the depth of going, and that will kind of, affect the accuracy of the solution. It's not all or nothing. It's not zero value, zero accuracy versus full accuracy. Right? And so this way of thinking about things actually allows us to think about online search, which is what I want to spend little time on for the rest of the class, actually. Okay? So, as I said, we have talked about fully deliberative agents till now in this course, because agents who wait patiently while you are figuring out what's the best plan so that they can make the first action in that best way. Okay? And we can also talk about fully reflexive agents, because it doesn't require that much. You just write a bunch of action, if then else rules. If this is the case, then just do this. And then they just do that action without caring about the goals. Okay, that's easy too. But this kind of an idea that we're talking about, it actually can use the available time to make a better decision. Now, one thing, now that we're talking about online search, one interesting point to make is online search can always get you into trouble. Not always. In the worst case, it can always trap you. Okay, people who don't look all the way to the bitter end and make the decision. So if you're making the decision, right now I'm making a decision without looking to the end of my life, I could be wrong in that decision. Right? I mean, people remember, this week was the Titanic disaster's 100th anniversary. Right? People made simple decisions in getting into Titanic. It looked like they got into the dining room and they said, yeah, the far away from all the noise, this real corner far away is a good place to sit. They sat there. And then when the Titanic sank, that turned out that that's like curtains for them, because they were the last people to get out of that car. They didn't look into all possibilities. They didn't decide what is the best, action given all probabilities thrown in. Right? So in general, any agent that does online search, you can trap it if you design a bad enough world. Okay? In particular, you want to talk about the set of words called ergodic words. It's a nice word. I may have mentioned it in the very beginning of the semester. But if not, this is a very nice technical sounding word that you can impress your friends with. Ergodic world. The world is considered ergodic if the probability that the agent can go from any state to any other state is non-zero. Given any pair of states, the agent can go from this state to this state with non-zero probability. Do you see what I'm saying? Okay. If you are in the ergodic world, then what happens is you cannot paint yourself into corners. Remember, people talk about painting yourself into corners? Now, why do people talk about painting yourself into corners? People don't paint themselves into corners if they thought ahead. And by the way, this is something that I should mention. I was going to mention last time too. You know, I have, as I said, I may have mentioned at different points in time that I have a son, and so AI people shouldn't have kids because, psychologists, I guess Skinner apparently used to put his kid in a little box to see and then kind of feed him to see how the things work out. But AI people tend to some extent, if you are interested in cognitive, behaviors and intelligent agency, etc., you tend to think in certain ways. I haven't been arrested by social services yet, so I didn't do particularly bad damage to him. But one thing I did notice, and I think it's true for you too, is as when younger kids tend not to do look ahead. They have the same model of the world that you and I have. But they choose to look ahead only maybe at one level. So I'm always surprised. Didn't you realize that this was going to fall off when you put this glass at the very edge of the table? Didn't you just think about it? Well, it's obvious to me because I'm basically thinking a lot before doing any action because it looks as if I have a lot of time. Whereas when you are young, you feel as if you must keep doing actions. You don't have too much time to look ahead. So much, this is my pop psychology. This is probably not completely, evaluated in any which way. But it does look like even if you have the same model as your dad or your mom or your granddad, you may still be not necessarily looking ahead because that takes time. And you're interested in doing action first. Okay. Anyway, so those kinds of scenarios, in those kinds of scenarios, if the agent happens to be in an ergodic world, then they cannot paint themselves into corner. Okay, so for example, we know that little kids, really small kids, we know they don't think too well. Not we know, we pretty much, I think, at least the ground truth seems to be that they don't necessarily go ahead and think about, if I do this, what will happen? They're mostly learning the models too. How do we make sure that they don't actually, in trying to learn the model, they end their lives, unbeknownst to them? We stabilize the environment. We make sure that in the living room, we don't put huge ditches where kids can fall. We don't put, small fires on the side and say to the kid, don't go there. We just don't put the fires at all. So we stabilize the environment. And when we come into the big bad world, by that time we hope that people have a good model of the world, and B, have enough patience to do right amount of look ahead so that they don't keep falling into ditches. If they do, we won't feel too sorry for them. We'll just say that's just evolution at work. Okay? But for the small kids, we stabilize the environment. And when we stabilize the environment, what we did was we took a world that's not necessarily ergodic in general. Real world is not ergodic. But there is no reason why your living room should also not be ergodic. Do you see what I'm saying? Putting a huge, big plastic, wrap would make living room non-ergodic, right? Because the kid will put it on his or her head, and for a while afterwards, they're unable to breathe, they can't remove it, and then social services will take you, to your rightful residence, right? So we just avoid putting huge, big, plastic sheets lying around. We do all our best to make sure that the world becomes ergodic. But in general, if the world is ergodic, you can do online search, and you'll only be inoptimal, finitely inoptimal. But if it is non-ergodic, you could be infinitely inoptimal, in the sense the agent may no longer be there after doing the wrong action. Okay, so in general, when we are doing online search, we take, this into account, that maybe that hopefully the world is ergodic enough that even though we are doing any limited look ahead, we won't die. In the chess, you may lose the game, and that's not the end of the world. If on the other hand, it's one of these Hunger Games or something, you lose the game or you die, that's going to be kind of a bad situation. Okay. So, coming back to online search, I don't know what happened to my thing. Yeah. Yeah. Now, before I go off into the online search, let me just mention this. This is the last slide about the deterministic games. I mentioned this already. This is just a summary of the status of deterministic game trees. Search in deterministic games. These games are called deterministic because each of my actions has a deterministic outcome. Okay, you can also have non-deterministic games where I first have to throw a dice, and based on what it says, I get to make my action. So even my action is not deterministic, or stochastic. Okay, so in the case of deterministic games, this sort of gives you a feel for where the state of the art is. And this is actually from XKCD. It's one of these sites that I'm sure you guys know a lot more than I do, which has like a cartoon form of, this is much more recent, a cartoon form of where the games, where the different games are. Okay, and there are games where basically there's no point in playing against the computers because they're too good, to games where there's no point in playing against the computers because they're too bad. Okay, and then chess is sort of in between, kind of in the right level for a while at least. Okay, so you could look at this later. What I want to do with the background we had about online search and min-max computations, to go away from games and start thinking about games against nature. Okay, so here is a little example. This is almost going back to beginnings. I'm at the start state here. I want to reach. I want to sort of go here. Let's say this one, I'll get some reward of +1. If I go here, I'll get a reward of -1, which is kind of bad. And then these two are states such that once I get into those states, I don't get to do anything. I'm dead. I can't come out of it. Okay. The actions I have are essentially, of course, as you might imagine, go up, go right, go left, and go down. This is an extremely simple search problem, and A-star search can do very well on this. Right? Okay? My question is, suppose I have actions which have actually uncertainty thrown in. So for example, if I try to go up, I will go up with 0.8 probability, left with 0.1 probability, right with 0.1 probability. And my model has given this information to me. Where whoever described the actions, remember you wrote PDDL specifications for your domains, so you would have written this as part of that specification. Okay, if you don't have it, you will learn it. Okay, but let's assume right now we are looking at the inference, and so this action has been given. It's the same thing. If I go like this, I will get 0.8 into this, 0.1 into this, and 0.1 I'll stay here. When I try to go this way, since there's a wall, I just stay here. That's the assumption. Okay, so I have a problem here, right? Now, basically I'm at start state. I want to know what's the action I should take. What's my first action? Should I go up? Should I go down? Should I go left? Should I go right? Okay. So I drew a little search tree, which here, basically, right? So in this particular case, actually, instead of being at start, I'm at 3, 2. So I'm in this state. If I'm in this state, I can, of course, do all actions. The reason I put myself in this state is I can do all 4 actions, just to show you a bigger picture. Okay, so here I can go right, okay, I can go up, I can go down, I can go left, right? And then if I were to go right, with 0.8 probability, I would be in 4, 2. 4, 2. With 0.1 probability, I would actually be in 3, 3, which is this. And another 0.1 probability, I will just remain where I am. No, with another 0.1 probability, I will be in 3, 1, which is here. Did you get what I'm saying? So I'm here, and I'm trying to go like this. With 0.8 probability, I will actually get here. With 0.1, I'll get here. 0.1, I'll get here. That's what this picture is showing me. think of this as the board position. Since you came from the game trees, think of this as a board position. You were in this board position, 3-2, and presumably you took this action. So if you take this action, you will get into a new board position. As to exactly which board position you will get into, you don't know. It's not up to you. It depends on these probabilities. Okay? And the same thing I can do it here too. Now if you look at this picture, first of all you realize this sort of looks like min-max tree. The only difference is I put some numbers here. Right? I put some probabilities for the outcomes. But basically, if it's a min-max tree, then I must have an opponent. Who is my opponent? Nature. Nature is my opponent. Now the question is, how do I evaluate how good this move is? I have to figure out how good this move is, 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 and then pick the move that will be giving the maximum value to me. Right? Okay. Now, notice that first of all, I could also talk about the entire min-max discussion here too. So I could have then gone further down in this, further down in this, further down in this, until every node is a leaf node. I mean, it's a terminal node. A terminal node means a node from which you can't come out. So in game trees, after the game is over, you can't keep playing. Like for example, your opponent says, hey, look, you're checkmated, you're out. And you say, no, I still have a lot of pieces, I'll keep moving for some more time. That's not allowed, it's dead, the game is over, right? Okay, so the question is, you basically could expand this all the way. The simplest idea is you can expand this all the way such that every leaf node is a terminal node. If it's a terminal node, you would know its value directly. If you know the value directly, then you can somehow back it up. And based on the backed up value here and here and here, you will pick the one that's the best backed up value for you. So now you are doing actions the way you are doing game actions. Now you're considering nature to be your opponent. Now the question is, how do you back up? And of course, if I don't go all the way deep, I could go just partially deep like here. And then I could apply some evaluation function here. What could be the evaluation function? It could be the heuristic. Right? I could just do the straight line distance of each of these to the nearest good-looking state. If it's in fact a single goal state, then what is the straight line distance to the goal state, for example? Okay. Another thing you could do is you could just consider the immediate reward of being in that state. Okay, so here this immediate reward is -1, this is +1, and I might just say every other state has just a small negative reward for being in that state. Because you should have been in a ending state rather than in this state, so you're dilly-dallying, you get a small penalty. So I could have these as the numbers. As for my leaf nodes, I could have some other better valuations. Whether, how do I get better valuations? I'll use heuristic functions. So it somehow connects this problem back to our A-star search and our heuristics problem, except all I need now is how to back up. Right? Okay. I'm sure you already know the answer. You would say, probably, that I will back up the value here as 0.8 times -1 plus 0.1 times -0.04 plus 0.1 times -0.04. That would give me the expected value of taking this action. And then I'll get the expected value of taking this, this, and this. And whichever gives me the highest expected value, I'll pick that action. You see what I'm saying? Okay. Now I could if I want to be more effective in my decisions, I could either improve the evaluation function such that it becomes a perfect heuristic, or I can go deeper. Not all the way necessarily to the terminal nodes, but at least a little deeper. And then back up using this expected value. That way too, you will improve your performance in terms of the decision you make. This is online decision making. You make one action, and then when again I ask you, what's your next action, you'll make the next action. And so you'll basically buy breathing time. You'll never compute, you're not computing my optimal plan yet. I'm just doing it action by action. And since you only want one action from me at every point of time, this is fine. Okay, now, if you look at it this way, the interesting thing is that what you thought, which is basically take the expected value of this by multiplying 0.8 by this and 0.1 by this and 0.1 by this. That's a rational position. Okay? You could actually have a different view on the world. You can say nature is your friend. God is out there looking for you. And so it doesn't really matter. I can close my eyes and all good things will happen to me. If you believe that, then who cares about the probabilities? Probabilities are for bozos who don't believe in God and God is not looking after them. Right? You are the good guy. So clearly, since God is looking after you, whichever of these has the best value, that's what will happen for you. Right? That is max. That's it. It's called max propagation. Okay, so this one is expected and max propagation. The rationals do expectation here and max over their actions. And the chosen ones do max because God is working with them. And then there are atheists and paranoids who think pretty much, I'm sure the nature is out to get me. Right? Right? I mean, it's true that they put this 0.8, 0.1, 0.1, but the 0.8 is for the other people. I know for sure that the least likely thing which will cause me the most damage will occur to me. So I'll do min. So in which case you get min max. So I'm looking at the same picture and I can get game tree if I assume nature is the normal game tree, if I assume nature is my opponent, and who knows that I exist and somehow cares about me and wants to do the maximum damage to me. Then you will do min max. If you think nature is my opponent and nature knows me and it likes me more than it likes the rest of the people, then you do max. And you think nature doesn't care that you exist. It's just doing these probabilities. You learn these probabilities over a period of time and it's just doing these probabilities. And so you do expectation maximization. And if you do this, which is basically this case, you essentially have a way of making decisions. You have a way of making decisions under online scenarios. So if I give you, a problem like this or any other problem which has stochastic actions, and I say, you only have this much time, tell me what's your first move. You go look ahead, some k deep, based on the time you have, you go k deep, look ahead, back up using expectations and maximizations, and pick the action that is the best action that you should do it. Once you do it, then nature will actually do its thing. And then you know which state you got into. Then you do the next action by again doing the same action, by again doing this same kind of a decision making. And so, in fact, even in domains where you have the full model, and if you have all the time, you can do full look ahead. If you have time constraints, it's better to do it this way. And if the version that I mentioned here, this one which takes basically these expectations over the values here, and then maximizations over the action choices. Because this is your choice. I'm sorry. This is your choice, and this is nature's choice. And in the game trees, this is your opponent's choice, and opponent basically will do the maximum damage you assume. That's why you be conservative. In the case of nature, you assume it is completely oblivious to your existence, and it just does whatever is whatever is probabilistically determined, and so you should take expectations. Okay, If you do this, this is called real-time dynamic programming. Real-time dynamic programming. That just happens to be the name of this particular idea. It's a good idea, right? I mean, it's not that hard to implement this. And you can take pretty much any, arbitrary stochastic action scenario, and then all you take whatever time you have, use that to go as deep as you can, and make decisions. Now, the interesting thing is, this we got here not by thinking of single agent, but going from single agent to game trees where there is single agent against a perfect opponent, and going from there to single agent against nature, which is again single agent. Right? Okay, so this is almost surprising that the insights for single agent search came from multi-agent search. But this is happening even now. In fact, some of the best ideas at the state of the art in these areas involve essentially what are called Monte Carlo search ideas, which were first basically found to be useful in the game Go, which is now the next frontier for the game tree search, because chess is dead and gone, and Go is still too hard, and all the papers are written on actually how to do moves in Go. And there are certain ideas in Monte Carlo search that worked very well in Go, and now everybody is busy applying them to planning, single agent planning. Okay, so this is not, although I came to it because of the way I structured this course, almost fortuitously. In fact, this sort of a cross-fertilization between multi-agent search and single-agent search is actually happening in reality. So the other point to make here is, suppose there is this question, as to how do I put the evaluation of these leaf node states. If the leaf states are terminal states, you know their evaluation for sure. If they're not terminal states, then you pick some heuristic value. And two heuristics I suggested is you can actually take a heuristic, like straight line distance or something. Okay? Or the other is just take the immediate reward of being in that state, which is pretty much what people almost tend to think. Okay, I go here, I go here, I go here, I go there, it'll be nice and cool there. It's not necessarily that it's the best of the world, but at least it'll be cool there. So the immediate reward of that state is good. Okay? So I give that as the value of that state. It may well be that it's cool because it will become cooler and cooler and cooler and you'll freeze to death. But to realize that, you need to go multiple steps ahead. Okay? So even if you take immediate reward, when you back up, at least you will improve your accuracy. Now the question that I have, I'm talking about this, is the following. So suppose I have a value right now is 0.1, -1, okay? And then based on this, I decided, let's say, to take this particular move, and I came here, let's say, this is what the nature did for me, and I came here, I do more search, and eventually I might find backed up value for this node, which is different from my current evaluation. To the extent I believe backed up value is a real value, is more real than the evaluation function value, I can remember these numbers. If I'm thinking of these as the heuristic values of these states, I have a better heuristic when I went deeper below that node. So I can put a huge big hash table of states and their heuristic values. If that hash table for a state has null value, that means I'll compute the evaluation function then. If I have a better value, I'll put that value into that hash table. And whenever I need to look up the state's value, I look at the hash table. If I were to do this, and I can do this here or in the game trees, then I'm doing essentially learning as part of search. So I'm learning the values of the nodes in addition to just learning what is the best action to do. And if you do that, then you do learning real-time dynamic programming, LRTDP. Okay, right? So in this case, I said leaf node values have been set to their immediate rewards. I can do better if you set them to an estimate of their expected value. And then I had, okay. As I said, you can, I may have written somewhere that learning part, but I may not. Okay, and in this example, for example, I may have an evaluation function for C in the beginning. Then I'll go one level deeper, I get a better valuation, so I remember that. I'll go one level deeper, I'll get a better valuation for C, I'll remember that. Next time around when I get C, then I don't need to use the evaluation function, I can use the remembered value, and I would do better. That's sort of related to, you may not be able to completely avoid the work that you did in the previous iteration, but at least you can improve your heuristics, evaluations of the boards, because last time around I realized, even though I didn't take that particular branch, I went below that multiple layers and figured out that it's only this good. And so I'll remember that number. Okay. So we did game trees. We went from game trees to using the same ideas to do real-time dynamic programming. Okay? And what I want to do now is to complete the circle fully and say, having to do online decision has nothing to do with whether there is uncertainty in the world. Okay, so we did online in both games as well as the real-time dynamic programming because either you are playing against an opponent, so there is uncertainty as to what the opponent would do, okay, or against the nature, in which case there is uncertainty against as to what the nature would do. Well, if I know how to do RTDP, if each of the actions has exactly one branch below it with 1.0 probability for that branch, is that still RTDP? Yes. It's just a special case of RTDP. Except now you are searching in deterministic words. It's not stochastic, it's deterministic. So now it would be RT A star, real-time A star search. I don't know if this is enough confusing or not. So I'm basically saying there is no reason why you could not have used these ideas for A star search. Whatever I told you can be used for A star search. Okay, even if in fact there is not, so whether there is uncertainty in the world and whether you are required to make online decisions, they are not one and the same. They are not perfectly correlated. In fact, one can argue that chess is a fully deterministic game when playing against the opponent. There is no uncertainty. And yet, there is time pressure. You need to make decisions fast. And the same thing can be done in a star search. So I have a completely deterministic world. Each of my actions has, I'm still playing against the nature, except the nature is deterministic. So for each of my actions, it has exactly one outcome. That makes the tree narrower, but it can still be deeper. Right? Instead of running a star search until it computes the optimal path and then find the first action, I can use these kinds of ideas to figure out what's the first action to do. And then do it. And then what's the next action to do? And then do it. This is basically you give yourself a little bit of time to make each of the decisions. Okay? And this is called the idea of real-time A star search. And so here, for example, I'm in the start state here, and this is state N, M, K, and I want to get to goal G, and these two states are closed. And if I want to go, if I go right, I go right. If I go down, I go down. There is no uncertainty in this domain. But if the state space is big enough, you'll still have hard time making an optimal plan. right? So what I might do is I'll just do k step look ahead. So I'm in S, right? I can do the following thing actually. I'm in S, I can go, the only actions I really can do are I can go right, I'll get into N, I can go down, I'll get into M. So I can go up, in which case I'll just stay there, I'll go left, I'll stay there. Right? So then I have two states. If from S I can go to either N or M. Right? Okay. Now, here's the interesting thing. N has the G value 1, and I might have some H value. H value might be just the number of moves to the goal. Number of possible moves, like straight line distance kind of an idea. Or Manhattan distance. Manhattan distance idea. So for N, Manhattan distance to G is 2 moves. So F is 3. That means you think if I go to S, go from S through N to goal, the cost would be 3. Estimated cost. If I go through M to goal, the estimated cost also would be 3. So at this point, if I were to make a decision just based on this information, I toss a coin and pick one of the options. If I have a little more time, I will go deeper below N as well as M. Okay? When I go deeper below N, I will realize that N is basically stuck. Right? From N, you can't go anywhere. You can only come back to S. In fact, there will be one branch with respect to S2, but that whose F value will increase. Okay? And then on the side of M, you can actually go down to K. I'm sorry. So in fact, in this case, I did show the S, but you actually should show S2. But let's assume that you are not allowed to go back. So then, N basically will lead me to this state, whatever that state is, whose cost is infinite. I mean, that means cost of going from there to the goal is infinite. Okay? Whereas if I am in K, the cost of going from K to J is 3. 1, 2, 3. Okay? So now G value is 2 because I made 2 moves. H value is 3. F value is 5. So I have 2 F values here. And you essentially do just, you basically, if I have 2 deterministic actions, I take the action that has the max backed up value. Okay, so in this case, because this is infinity, and this guy's true F value is the minimum of the children's F value. It only has 1 child, so this guy's true F value is infinity. And this guy has only 1 child, so its true F value is actually 5. So then you can go this way, you will have an estimated path of cost 5. You can go this way, where is an estimated cost of path infinity, so which would you pick? Since it's cost, you do min of the cost. It's the same idea. If you have 2 actions, and in the previous case, in the RTDP case, we talked in terms of value of the state. Here we are talking about the cost of the state. If it's cost, you want to minimize. If it's value, you want to maximize. Okay? So if you take the minimum of those 2 F values, you would wind up taking M. In this case, that is actually the optimal first move to make, right? You can't be sure that this will always be the case, because this could have been a much bigger game tree, a much bigger tree, and then, essentially, it's not obvious that, maybe there's another way of getting out of N, even if it's circuitous. But if you are doing, this is depth limited. Here the depth is being limited. I know that we talked about depth limited search in iterative deepening, depth first search, and depth limited search. But there, the idea was still to find the entire plan. Here you are doing this just to reduce the decision cycle, time taken to make the decision. And you are improving the time taken to make the decision, so you're shortening it at the expense of quality of the decision. And if you have more time, you go deeper. This would be called RTA star, real-time A-star search. It was separately invented. So in fact, in AI, RTA star was a separate paper, RTDP was a separate paper, and min-max stuff was a separate stuff. And then the community slowly realized they're all connected. Since you were born after all that confusion, you get like the more coherent story. Even though it doesn't look like it's a coherent story looking at your faces. Okay, right? So it's all nicely connected. Okay, game trees are connected back to single agent search in deterministic worlds. And then one last thing, of course, is now that M's F value, previously I thought was 3, but then when I backed up, M's true F value seems to be 5. So I'll have a hash table and put M, and in that hash table, if M exists, then I'll read off its heuristic value from there. If not, I will compute it. If I do that, then essentially anybody whose heuristic value has already been improved because of look ahead, you would use that next time around. If you do that, it's called LRTA star, learning real-time A-star search algorithm. Okay, and both LRTA star, LRTDP, as well as the min-max search, these ideas are actually very easy to implement. Compared to GraphPlan and all this stuff, these are much easier to implement. And basically, the deeper you go, the more work you have to do, and you have to decide how deep to go. All the interesting theory is what is the way, how deep to go. And since I mentioned earlier on, I mentioned to you guys the Monte Carlo search in Go, and since you're already far gone and you've gotten too many ideas crammed in, one more idea isn't going to hurt, and which is that all these ideas today, I talked about going deeper into the tree. Another way of thinking about it, this whole thing is I have a whole tree in front of me. I'll just make one probe through one branch. Then come up, make another probe through another branch. Okay? These are all, each of them are full samples. If you do that, you also get estimates of goodness of the action. So in particular, suppose I'm here, right? I'm in this action. I'm trying to decide between this action, this action, this action, and this action depends on this state, and this state's values. To figure out the values of this value of this state, I'll just simulate in my head, doing a bunch of actions starting from here, and see what happens. And if I reach a good state, that would be the good value of that on that particular sample. And I'll again simulate one more sample, see how good that is. And I average my performance over all these samples. This is essentially, here you are trying to do search not by increasing the depth of the entire tree, either uniformly or non-uniformly, but by making probes into individual branches randomly. And when you do this, you can then essentially wind up getting bounds on the values of these states, upper and lower bounds on the values of these states. And if you use those bounds, that's basically the current nifty ideas on using Monte Carlo search. There's an algorithm called UCT, Uniform Cost Trees, I believe, which basically, upper confidence bound trees or something, which actually keeps track of the confidence of the value that you have of a node based on the samples you have done. And then it does more sampling under certain nodes because it's not very confident, and does less sampling on certain nodes because it's very confident of its answer. Again, give you 10 minutes, would you put it all equally across all branches, or do you do it dynamically? Okay, and all of these become important because in an online search scenario, you don't get to say, I will wait until the answer comes, because that will be too long. Okay, UCT will certainly not be asked anywhere on your things. You might look up UCT, however. Okay, and whatever we discussed today is actually you can use these ideas to write simple game playing AI programs. pursuit and evaluation strategies, etc. Okay, I'll end here. As I said, I will send you guys a mail about interactive review. You need to make sure that you put your inputs onto the blog before you come to Tuesday's class.